I looked up the show. He picked up the friends and type. That shining the chicken. And it's jump with the place. Big, like the around those to be good speak of this teacher. We include the vices with the council. I neglect music. Then time to choose it and do it. Yes. Then it's that's a okay. That was not that was it's a height. That's was nothing that's telling for this and ten that is children. I children there was some wasn't teacher things I did. I laugh about the thing. Like have it like one music into it. It's really good sitting in still not as because it's the most time. Can you get that joke? I can do what would typically worth listening to your tune. It's until the beach and the bitch. That's it. The joke. Come to see it's to its applicants' reputation. It's a right to each survive the thing. The shaman for the just so they can up things. It's but for search. Okay, so just go ahead and update them up to look in that she's that should just be what is this that then the done just in the like just to because okay but yeah since I've done you get to it's really good your article since I've been so you just take fresh and next like you said so with it very sweet it's in this we're going to tell things I left just thinking tonight there's a little snack to this savor for me your is the prohibition yes that was it yeah and you know doing it so doing if it's in the water to get it and to find me because it probably I let's stay on it in okay this is this week system you just and it sometimes it different phase, but that's not this real. So that's then it's that you chat with yourself, your scholars to do it. You do these things that and this is just the activity that goes it's just a like that it's a really state I didn't satisfy but was it this and I had to do this really that to now it's better and it's good but she's on that meeting with it we caught this chicken this figure on 10 things that you know it but we caught it anything that you took that favorite actually okay this new course was it's like 2 minutes of that. When you can, you're spending like about 3 hours to this channel. Oh my God. It's like the new thing about it. To me. So this, so the really when they pass, it play and you let that. Get this thing. It's like told them what needs to grow and how best you share. With this, that's right. Like that. This is the best. She moved it, but the wood. That's a page. It's not and set it. And that's it. That's the good tip. It's not actually. You got it. myself it could team of the thing just dialects today in this no. Obviously, yeah, I feel like my regular. It's a trigger. There are nice days with it up there. Yeah, different also. Space. That's a good getting to be true to find it out this one. This set with this. Okay.
Calculate the corrected accelerogram, and from the corrected accelerogram take the S wave portion, and say suppose 10-second window is fine. Take the S wave portion, take the S wave part, have the Fourier transform that things has already been told how to calculate Fourier transform, and I had given you the code. So calculate the Fourier transform, and then also you can take the both the north south and east to west and make it a square, and take the square root, calculate the horizontal spectrum, and also take the vertical one, divide the two, and calculate your HVSR ratio, because I have not given you any rock site station, so you cannot calculate SSR, but you first calculate your HVSR for the data with your, so all the amplitude spectrum, how to calculate amplitude spectrum and the noise spectrum, these are all shown to you, so you can now can calculate these data, right? So, and also in the baseline correction, you can see the baseline correction. So the baseline underscore GIN, GIN, that's the main program. So I had put one simple, because from the data last time I had seen the K220 has a very high drift in the vertical component. So I had seen that H2, that vertical component data, I try to put it and run the code. Then if you have run the code, then you will be seeing that the vertical component now gets stabilized. So the acceleration part is basically corrected, right? So the corrected accelerogram, you take the Fourier transform, do the things, and find out how does it looks like. So that's your work today. Make sense? So and also I had posted the stochastic simulation. You can run the stochastic simulation, only you need to change the magnitude as well as the distance, and the distance it will calculate and give you time series data. You can run it and check it out. Okay, only change the magnitude values and the distance. So check the code and find it out. Okay. If you have any questions, let me know. It might change. It might change. It might change, because a sampling of the big part and big sampling of the small part, the fundamental frequency will change. Yes.
Running this code, sir.
Mm-hmm.
It's showing that W_4 appears to be unused.
Have you put the W4 my FFT in the code?
Yes, sir.
What is this? Why you are getting these things? But where you are getting?
69, sir.
60?
Just a minute, sir. Line number 69.
Line number 69. Where is the 69 is the, yeah, below. Okay, let me see. W4 is this. But the W4 should have come from the my F50 part.
This exercise has to be only for K2 to 0 because this
But you can do for the all the three. Yeah, so it is coming from here, right? Because my F50 is there. So what does happen? It should.
This is based on, sir. This your course.
Uh-huh.
This is the course, sir.
No, that's okay. Yeah, but your 69, if you are going to the 69, what has happened?
Just a minute, sir.
Where is that code?
69.
So 69 and they are giving the error here first. What is this? Time equals to, there should not be any dot dat.
Because, sir, the file is 29 is dot dat.
No, that's your reading, that will be the dot dat. But whenever you are doing the calculation, so where can I get the again? So go ahead. Here. So this is
Change this one there.
yeah. So this is load fine, but this is only the whenever you read the data, this will be not that. So this will be the without that. Make sense?
Okay.
Yeah. So there is nothing dot that. Okay. Just try and run it now.
Sir, on the occasion of Independence Day, like, are we going to have?
We are not independent. We are dependent on that day. So they had not given us the independence. And I will not be teaching on that day. It is Professor Agarwal will teach on that day. So don't ask me. I am fine. I will have a independent
No, sir,
things.
actually we were thinking if maybe we can have half day for celebration.
Yeah, we were thinking on that. So you need to ask Professor Agarwal on that, because he is planning the entire thing. So
No problem, sir.
I told that we need to go with a line and we need to unfurl the flag and say Jana Gana Mana before coming here. So we need to do that. Every Indian need to do that.
Invest how you want with no
So everybody understood what you need to do, right? So basically you have to calculate HVSR for these 3 sites, okay? चला गया the power is there, right? Yes. Yeah. Internet issue possibly. Possibly. I don't know. Because otherwise, why it will go? It can get off, but screen can get off. 59. What is this?
Plot n time win underscore data comma n time underscore data. Just as habitual.
And whether the values are not there. Do the either in-tapered data array or n-time win data array, nt win data.
Okay, okay. Yes, W is capital, here is small. I will check certainly.
Yeah, so that might be. Done?
Only some change I mentioned SW. Here in the notebook it is written as S capital SW, but showing error, so I remove S. So
Oh, okay.
So this is your noise of that particular set. It also includes instrument noise. So all noise is here only.
Yeah,
This is your signal.
signal. So now you do first the correction, baseline correction, and then you do the same thing. Okay, so then it is a corrected. Yeah, and what is your question?
So suppose if we get such type of HVR spectral ratio, so how we will interpret?
No,
this?
we will be taking this time this one because
this one.
not this one. The
So this
taking
is your fundamental.
might be that because this might be the one spurious one, So we should take this part.
And sir, what about this range?
This one is not. This one is.
This your fundamental.
Yeah, this will be fundamental because this might be the spurious things. Yeah. So what has happened to you? So first you correct it and then you plot the things. Okay. What is that?
HVSR, sir.
Hmm?
Final HVSR.
HVSR after correction?
Yes, sir.
Really? Mm. Um,
With 3 components, sir. Then tapered
and this looks to be pretty high. This is which site? No, just put it here. Let me see.
K209, sir.
K209.
Yes, sir.
Okay. Put it for the K220. Just try to see the things.
Sir,
It looks like to be very, very high value. But let us just show me the plot. Make this frequency also the linear.
okay, sir.
Make the frequency linear too. Just plot up to 10.
Up to 10.
Okay, just plot up to 10. Mm. Okay. So what you need to do is basically uh, we need to smooth the the data a little bit. That the Fourier transform need to be a little bit smoother more. Then it will be okay. Mhm.
Okay.
So try. Might be that peak is a little bit spurious peak. If you show me the Fourier transform of this one, means you have already plotted the Fourier transform, right? This is your time window, and so this is your spectrum for this one, right? So why it is not moving? Oops. Now I'm trying to see. Have you used any smoothing parameters to?
No, sir.
No.
Firstly, we have done the cosine, cut the window of
Yeah,
seconds,
yeah,
and
yeah.
after that cosine tapering, and after that FFT,
Yeah.
and after FFT main of node south is stress,
Yeah.
and after that divided by the vertical.
Vertical component down. So
Yes.
then you do, if you see that in the code, whatever I had given it to you,
Yes, sir.
but there is a move mean. It is a move mean part
Okay, sir.
where you have some little bit smoothing is there. No, not this one. No. If you can go to the folder today, I have sent it. If you can go to the folder today,
Okay, sir.
and there is a in the Fourier transform part, there is a bottom part. There is a data smoothing is there. If you can go there. No, you have not downloaded that. You just go to the Google link. So there is a no. That's the Fourier transform folder. You go to that. No. Yeah. Fourier transform folder. Just you click it. Click that. Click the folder. Yeah. Okay. So where is this? Oh. Yeah, so if you can see the swspectrum.m, swspectra.m, just you open it, swspectra.m. That's okay. It's okay. We got it. So if you go down, go, end, almost it, almost end, go, almost end. There is a, oh, have I uploaded the wrong file? Let's see. Oh yeah. So this is a smooth thing. So So make it a little bit smooth, and then that will looks okay.
Sir, while doing the FFT, we have to smooth the FFT spectra, sir.
Yeah,
First,
yeah,
and
yeah.
after that we have to
Yeah,
calculate
yeah,
the
yeah.
using
To-
this one.
using this one. So basically if you run this code, you will see that there is a smooth version is being plotted. If you, because you have this data, right? Let me go to the top. Let's.
I have to go, sir.
No. You have to go to the top. Go top. Go up. Oh, this is the different data sets. So if you can put the data sets and then run our own data sets, if you run, then you will be seeing that they are smoothing it. No, you have to change both the time and acceleration data too, because that is a totally different. Yeah, that is also K209 time history and.
Any other change, sir?
No, I think so. It will. Yeah, you can now put some cursor in somewhere.
Yes.
Yes. Yeah, somewhere. Yeah, that's fine. No, I think this is for the both. When you have to put the noise and the S. So go to the noise side also. Yeah, go to the noise side and then also take this S side. Yeah, and take the S side. Yes. Check it out. Yeah, you can see this. So there's not tapered signal, and then
Tapered signal data, tapered noise data.
and then there might be more.
Okay, sir.
Let us see. Yeah.
This is the baseline corrected signal, so this is the tapered and this is the tapered signal value amplitude spectrum.
No, this is not.
Run it again, sir.
This might be.
Some other values are also
No, there is what? Oh, they have some
undefined function of variable.
SW4. Oh, there might be some wrong value is there. So I have to check that. I should have checked that. So can you go to this line 974? Oh, this has to be the W4. You can make it a W4 instead of a SW4.
Numerical addition.
No, this is W4. Just make it a W4, not the SW4.
Okay, sir.
Just make it a W4. This value. Yeah, let's run it again. Just go to this one. Take this one. Yeah. Take this one. Yeah. Fix it.
This one, sir. This one, sir.
Mm.
This one, sir.
Yeah, you can see they have plot the Nice. Then that will be giving you a smooth
Okay, sir. We have to smooth the spectrum
after
like this one.
like this one. So then
After
then
that-
your HBSL looks to be very good.
Okay, sir.
But you have to do the vertical also.
And on every component we have to smooth the spectra like
Right.
this one, and
Right.
after that
Take
we have
the-
to calculate that VSL.
Right. That will be better.
Okay, sir.
And you need to first correct this one because that is giving you the bad noise.
Yes, sir. Yes, sir.
So correct the first the recorded data with your baseline correction.
Yes, sir.
Then you take the
Then,
Fourier
yes.
then take the Fourier transform.
And after when we are calculating the Fourier, after calculating the Fourier spectra, we have to
Smooth the data.
Okay,
Yeah.
sir.
Okay.
Thank you, sir.
So what are the study of your 3 musketeers? Any improvement? आज तो कंप्यूटर बंद नहीं होना चाहिए. So what about yours? You're trying? So, any nice plot?
Yes, sir. I have got beautiful plots.
Beautiful plot.
Yes, I'm redoing it because I mean the baseline correction is a new thing.
Mhm.
So otherwise, the old one I got was this one. Steps. And the steps I was following, I got this one. So then sir was telling कि इसको थोड़ा और करना पड़ेगा.
Mhm.
So this one was yesterday's one
Okay.
that I had updated. तो इसको थोड़ा और ऐसा करना पड़ेगा.
ठीक है.
Saturday.
करो करके दिखाओ. So what about yours? Oh, इसके साथ कर रहे हो? अच्छा. तो आपका कुछ मिला? मैंने anything good for you?
Oh, sir. First, this Python, I'm not so good at it.
Okay.
So-
You have to translate it in the
Yes.
Python, right? Okay, that's fine.
So I converted it into MATLAB,
Hmm.
and then I have done this correction.
So correction now looks good, right?
Now it's
Hmm.
okay. After correction,
Then you take the Fourier transform. Yeah, then you take the Fourier transform.
we have to take that S.
Right.
S.
S and this one, and then smooth the spectra with the move mean, and that will be better. फिर बंद हो गया. तो आपका उधर चल रहा है? It's working on this side, but this is closed. I don't know. এটা বন্ধ হয়ে গেলে কি এটা বন্ধ হয়ে যাচ্ছে নাকি? ও ও ও ও এটা off নাকি? হুম। চলে যাচ্ছে কেন আমি সেটাই ভেবে পাচ্ছি না। ইন্টারনেটটা আবার কিছু প্রবলেম করছে। ওখান থেকে চলছে।
এটাকে কেটে অফ করে আমরা
Someone is not connecting.
ডিসকানেক্ট করুন, কানেক্ট করুন।
দেখি ওটা ইন্টারনেটটা দিচ্ছে কিনা। কানেক্টেড সিকিউরড, দেখি এটা গুগল আসছে এসছে। So I had put some of the folder. Oh. So I had put some folders in your Google Drive, and you can check that. I had posted one folder called Fourier transform, where all the Fourier transform, how to calculate the Fourier transform from the files is given, right? So might be you need to change the file name because that's a different file name we have used. And then I also included in that folder what I called it's a baseline correction things. So baseline correction, there is a baseline correction .m, and then there's a baseline underscore gan.m. So the gan.m is the main program. Baseline correction m is the function subprogram, right? So that is there, and then also I have posted there that the stochastic simulation, that means whatever we have done yesterday, that stochastic simulation code I had also posted here. Now, so mostly the tools are ready for you. So now what you need to do is to basically calculate from the files, that 3 files, whatever I had given to you from these 3 files, you need to calculate all the response spectra, Fourier spectra, the baseline corrections, and all these things, right? So these are the things you have to now do. What I am trying to ask you is to do this. Before I tell you what are the things you need to do now, I need to give you a little brief introduction about the site response calculation from the time series data, right? So what are the 2 methods we need to understand is this, that if we have a station, as I was showing in the morning, that there might be a big soil deposit things where we have the stations, right? And this is your rock stations, right? So these are the rock sites. Okay. Now, each site you have recorded. Each side it is recorded the 3 component time series. Okay. So here we have a north-south record. Okay. So this is your north-south acceleration record. Then there might be the east-west acceleration record, and this is your vertical acceleration record, right? So 3 component record we have recorded here as well as also recorded here. So this is also north-south, east-west, and vertical. Right. So this is what we call it as a rock site, and this is what we call it as a soil site. Okay, so this we have, we might have a lot of soil sites, so that is fine. What is required, what it has to be, that my is that this is the earthquake which has happened, right? And from this earthquake, the wave comes here, and also the wave goes here and recorded simultaneously, right? With a lag or time, because that's this part. Now you have recorded the time series for this earthquake which has happened, right? So that's the case. Now if you take the time series data from here, and we need to convert it to take the Fourier transform of each component, and you will be getting the Fourier spectra of the north-south, the Fourier spectra of the east-west, and the Fourier spectra of the vertical, right? So that you will be getting from the time series data, right? And whatever we are talking about the Fourier spectra, we are interested is only the S wave part of the Fourier spectra, because the P wave part we are not interested, because this is a very small, and that will not damage any structures. So we are all interested about the S wave part of the data. So we will be cut the S wave portion of the data, say 5 seconds, 10 seconds, 18 seconds, 20 seconds, whatever you like to do, that you take it from here. Okay, and then compute the S wave part of this one. And similarly, you also do the same thing for the rock site station. Okay, so in the rock site station, you also do the north-south, east-west, and the vertical one. Okay, so this you have done. So this we do for both the stations, right? So both the rock site and the soil site station. Now, you know, as per our that stochastic simulation, whatever we have seen, so this is your observed spectra or observed S wave spectra. So you all take it granted that we are talking about the S wave part only. So if it is a observed S wave spectra at a given distance r, then that will be equals to, as we have done, this is your 1 by r, might be the r square if it is a body wave, then the source spectra, okay, and then there is a site spectra, source spectra, this is your site spectra, and then this is your path, right? So this is your path spectra. So this is the thing, multiplied the instrument factor, that is equals to your 2 pi f. So this is your observed for the soil site. Let's see, this distance is Rs, right? And this is also another observed with a rock site station. This is the same thing with a 1 by, let's see, Rr. That means this distance is Rr. And then again, source part will be find that part. Then there is a site of the rock site, and then there is a path of this one. Okay, path factor, path is f and r. Path is f and r, so that is there into the instrument factor here. Right, so if I divide these two spectra, that means the observed spectra at the soil site. Okay, let's write it with this observed spectra at the soil site and observed spectra at the rock site. Okay, at the rock site, if you can divide it, then basically, if you divide this one, then this part and this part get cancelled because these are the same source it is coming out, right? So if the RS is very, very similar to RR, because if this earthquake is located far away from the location of these two networks sensor, we can say that that distance is basically negligible, right? So we can delete this one also, right? So we can delete this one, and then also the path become also the same, right? So path is, because this path factor, this will be also be the same, right? So if you can do that, then basically this is your site factor of the soil site divided by site factor of the rock site, the site of the rock site. Okay, so that will be the case, right? So that will be the case. So basically, if you divide these two, that means observed located at the S and observed located at the F, and at the rock, that means individual their observed spectra, then it will be fine. Now, if we assume that it's a rock site station, the rock site station, the thing is like this, that the amplification or the site response, okay, so the site response for the rock site station, since it's a rock, I am trying to plot the frequency here. So that frequency, at that frequency, the rock site is not amplifying anything, right? So we will be assuming that rock site amplification is unity, right? So rock site amplification is unity because rock is not amplifying in any frequency, right? So if you can assume that successfully, sometimes what has happened, that the rock sites are the very near surface rock sites, there is a lot of wearing and tearing, and there is a fracture, and all these things are present at the rock site. So that might be introducing some of the amplification, and that amplification might be somewhere at the very high frequency. You might get some amplification, but within, say, suppose from 0 to 8 hertz or 10 hertz, you may not see any amplification if it is a pure rock site, right? But that will be, that you have to test, okay? Sometimes it will not be. So if it is not be, then you need to introduce that value, you have to put it for different things, different frequencies. So then if you can see that, then your site response of the soil site you can calculate is basically the observed the soil site, okay, observed spectrum as the soil site divided by observed spectrum at the rock site. So if you have soil and rock site, so if you have a data from the rock site, then you can calculate the site response of the of the particular site. Okay, so that we can calculate the site response of that particular site. So this is your site response calculation from the recording data from the rock site, right? And now let me tell you this one. Say suppose this is a some area. Okay, so this is an area where we have lot of network stations, right? So these are the stations which we all see. Let's see this. Some of them, or the one or two of them, are located on a pure rock. All other might be in a soil, right? So, and then the earthquake might happen here, and earthquake might happen here, earthquake might happen here, earthquake might happen here, earthquake might happen here. So with respect to station distribution, the earthquake has happened all over the azimuth, right? So from this, if we say that these are the concentrated at a particular point, so with that particular point, if you can go all over the azimuth, or if you get the data from all over the azimuth and then calculate the site response for each earthquake. Say suppose this is the site response for one earthquake at a particular site. Let's see this site. Then this might be the response of the this might be the response due to the another one, and all of them you calculate, and they will never be the same, right? So that will be depending upon the magnitude, depending upon the frequency, enrichment. There will be all different type of amplification, but whenever you take the earthquake from all over the azimuth, then it will be statistically it will calculate a very nice coverage, and then the waves are coming from the different direction. Particularly for, let's see, this station, we can calculate a logarithmic average of all the data, right? So that will be the site response for this site. Okay, so that we will be calculating with the standard deviation measured, or one standard deviation we can calculate from their data. So this is what we call it as this method of calculating the site response, we call it as a standard spectral ratio method. Standard spectral ratio method. So this is called SSR, standard spectral ratio. Make sense? Okay, now, so this is your site response, and since this is your site response, it's only a pure number, right? Because there is nothing unit, because this is the division of two same things, right? So this is a pure number, and this on this side it is a frequency, right? For any site classification, we always do the, say, from 0.1 to 10 to 15 hertz is mostly the required things. Okay, if you do not have any special need to do something high frequency site response calculation, we should not do that. Okay, now let me tell you one thing, that the site high frequency the higher the frequency, we are sampling the very shallowest part of the layer. So that means shallowest part of the soil. So basically, if you are going towards more than 15, 20 hertz, you are confining your site very shallowest part. Okay, something upper 1 meter or half a meter. If that is your lookout, then you should go for a very high frequency type of calculation. But if it is not the issue, because in general we should look at something around 30-40 meters on a type of thick sediments and its response, right? So that is what we are basically interested in. So we are geotechnically or from our seismological point of view for the site characterization study, we usually do 15 to 20 hertz. After that, no. Even the 10 hertz is fine. So this is what is called as a standard spectral ratio. Now, if you are doing it S-wave spectra, as I'm telling you that you are doing the S-wave spectra. Now, this S-wave spectra is because we have the horizontal component of S-wave spectra. So we are doing it in the sense both the north-south as well as the east-west, right? So north-south and east-west is the both horizontal component, and so we have to take the both part of the data, right? So what I have to do is this, that that we need to calculate the average of it. So we will be taking the observed S-wave spectra for the north-south component. So that things, so make it a square, and observed east-west spectra of the S-wave, make it a square, and then divided by 2 and take the square root, right? So that is your what I am writing it here as a observed S-wave, right? Or observed soil sample, observed soil F, right? So that means this is what we call it as a arithmetic average. You take that arithmetic average. Okay, so this is one way of doing it. On the other way, we can also do, some people also like to do, that means the observed north-south F and observed east-west F, and then take the geometric mean, right? So that is equals to your observed F. So this is what we call it as a geometric mean. So everybody has some preference. So somebody likes the geometric mean to do, somebody likes to do basically the arithmetic calculation is fine. Okay, so this way it can be done. So so what you need to do, okay, now this site response calculation has an advantage. It is very easy, and just only calculate the S-wave part and take the Fourier transform of that S-wave part, and then compute it just by 2 north-south and east-west, make it a square, divided by 2 and take the square root. So that will be the observed data, and similarly do it for the rock site and divide them together. So it is called standard spectral ratio, and we can calculate the site response. But please remember, this site response calculation has a limitation. The limitation is this, that if that earthquake, whatever triggered both the north-south and both the that earthquake has to trigger both the rock site and the soil site. If it has happened like this way, that the soil site get triggered and we can get the data, but somewhere or other the rock site is malfunctioning, we didn't get any data. Okay, that is possible. That always happen. Sometimes there is a electrical failure, sometimes this is some failure, and it always happens. So if the rock site has not been recorded, then that earthquake you have to throw it away. So there is no way you can do anything else, because you have to divide the data with the recorded data from the observed things, right? So that's a main disadvantage. So that means if the rock site is not recorded along with the soil site, so it has to be recorded by both the sites. Then only we can do the things. If it is not, then we have to throw it, that data for that particular station, right? Okay, so this is first thing. And so this is one way of doing the site response calculation of the things. Next part is that there is another way. Now, these particular things also require a rock site to be present. So that means in your area or where you are trying to do, you should get a station which is a rock site, so that you can compare the vibration at the rock site with the soil site. Okay, but if you do not have any rock site, there is 100 of area, or there's a lot of area, there is no rock site things. And also, please understand, the rock site should not be very far away from the soil site. Say suppose when a rock site is in Dhanbad and the soil site is in Goa, I cannot do that things, because the earthquake which has been recorded, it has a totally different path, right? So that path will be different. So if you have a one station at the ISM campus, other station in the Bankmore, other station in the Katras, might be, but not the very very far away. So that this assumption that we are multiplying with we are deleting R because of the proximity of the soil and the rock site with compared to the source, that has to be valid, because if it is not, then it cannot be calculated. So there will be fallacy. So that you need to understand, and the rock site has to be there. But as I told you, that there are a lot of areas where there is, that means this is located entirely in a basin or entirely in a big sedimentary areas. So there is no rock, there is no mountain, there is nothing. So what should you do that? Okay, and that is where we will be doing another method, and that is what we call it as a HVSR. Okay, so HVSR is another technique of calculating the site response. So this is known as a HVSR method. It's a horizontal to vertical site response. Okay, HVSR. So horizontal to vertical site response. Now, this is there is for these stations, for HVSR, we do not need the rock site. Okay, we do not need the rock site. So what has happened? So that means if we have a basin here, and might be this is this one, so that's okay. We can calculate. So this is your rock site, and this this is your soil site. So this is your soil site and this is your rock site. So this is your soil and this is your rock. So we again have a 3 component things, horizontal, 2 horizontal one, north, south and east, west, and 1 vertical one, right? So what I will be doing is basically HVSR is a, so whatever we have got the observed spectra for the horizontal component, that's this divided by the observed spectra of that particular site at the vertical component. So you just divide for this soil site, you just calculate the observed horizontal value. So east west square plus north south square divided by 2, and then the vertical component. So take the horizontal and the vertical component and then divide them together. So similarly, you can also calculate HVSR for the rock component. So take the horizontal observed value for the horizontal at the rock site, and observed value for the vertical things. So individually, but they are horizontal and vertical has to be divided. Okay. So that will be giving you also with the frequency. So HVSR is a function of frequency. So this is also a function of frequency, because this is your frequency things. So you will be getting a the horizontal means it's the mean of the both the north, south and east, west component. Take each square and divide by 2. So that's the mean value. Either you take the arithmetic mean or you take the geometric mean, whatever you wish to do, that's fine. Right now, if you so if you do the HVSR here, if you can plot this HVSR and this is your frequency, then this will be, you will be seeing a spectra like this. Okay, some sort of a spectra like this. Sometimes the spectra will be flat, might be, that's okay. That depends upon the thickness of this. So this is what we call it as a fundamental frequency. This is what we call it as a F0, or the fundamental frequency of the soil site. Fundamental frequency of the soil site. So that is their resonating frequency of the soil site, right? The assumption here is this, that whenever the earthquake, whenever this earthquake enter here, okay, as I said in the morning, that in the shake or it is a two-dimensional, one-dimensional, the shake analysis or the shake things. So what has happened, that this is what we call it as a vertically propagated S wave, right? So it's a vertically propagated S wave, propagated SH wave, right? So vertically propagated SH wave. Now, they can amplify they are amplified by the ground. So the horizontal layer, this horizontal layering can amplify the S wave or the horizontally traveled S wave, right? So that they can amplify, but they cannot amplify, but the vertical component do not get amplified by the horizontal layer. So So their response to the horizontal layer density values and the velocity values, their response is almost negligible. So that's why we always divide with a vertical component. So the vertical component has no amplification, but the horizontal component has amplification, right? So that is the main reason of dividing the horizontal component by the vertical component, right? Now, let me clarify 2-3 things. That the HVSR amplitude, this amplitude of HVSR, or the maximum amplitude of HVSR, what we call it as A0. A0 is the maximum values of the HVSR amplitude, right? That amplitude does not very well, or it do not reflect very well the soil site. So that means the site response. So that means that number is not very well reflected on the site response value. Or in other words, if you do a rock site versus soil site comparison, the HVSR amplitude and SSR amplitude, we will be believing much more on the SSR amplitude wise. So the site response, if you need to do, it will be better to do the SSR. But if you wish to calculate the fundamental frequency of vibration of the soil, then HVSR is the best result, because they will pinpoint the F0 value or the fundamental frequency of the soil sample or the soil layer under the place of investigation. They will be giving you more accurate values, but not the amplitude wise HVSR is not a very good indicator, but SSR does. So they will be calculating the site response much more better way, okay, amplitude wise. Okay, so this is the work you have to do, okay. I will be taking the lowest peak because that is your fundamental frequency. Okay, so that's the fundamental frequency. Others might be a harmonics on that, right? So that you need to. So we will be taking the highest peak on the low, that will be given by the low frequency value. So that's your fundamental part, and that is what we are interested in.
Suppose we obtain the lowest peak at the low amplitude.
Yeah, the lowest peak at the low amplitude, then take the low amplitude. That will be the better results. Okay, unless and until it is a spurious. We check for that whether the signal is not a spurious signal, but if it is a spurious signal, then this is possible, and due to the presence of the soil layer and due to the presence of the density or the low velocity sediment, you might have a different peaks in the HVSR. Okay, now this is one thing. HVSR is a very, very common and very rapid assessment of the site characterization, because just you need my two sensors, or just you need one sensor and put it at somewhere where you need to calculate, and then wait for the earthquake, and if they recorded it, then it's okay, then it will be your site response, or it is your HVSR values, right? So, and if you have a earthquake from different azimuth, with a good azimuth coverage gives you much more confidence in your estimated HVSR values. Because if all the earthquake coming from one side, then the directivity effect will be questioned, right? So basically the sample, that means that area has not been sampled from all the directions. So that might be a little bit either overestimated or might be the underestimated values. But if you have a good azimuthal coverage with respect to the site, then that would be good. Okay. Now, HVSR has or will be done in two ways. One is the earthquake record. So that means if you have an earthquake, you recorded it, take the S wave part, calculate the horizontal part, and do the things. So that is what we call it as a EHVSR, earthquake HVSR. E stands for earthquake, right? Now there are also HVSR studies are currently done, which is called microtremor HVSR or ambient HVSR. There are two things: either the microtremor, the very small earthquake, are being measured, and from there it will be the earthquake. It will be the HVSR can be calculated, right? This is one thing. The second thing is this, that MHVSR is also called ambient HVSR. So that means every time the outside ground is vibrating due to the noise, due to the vehicular traffic, due to the human noise, due to the, if you are in a coastal area, the waves hitting the coast material, they will be also transmitted into the land, and that will be also giving you the vibration which you can measure, right? But these are the what we call it as a MHVSR. So that is your microtremor or the noise HVSR. Now these are the surface waves type. So these are basically, the noise is basically, so we are doing it for the surface wave microtremor, a surface wave HVSR, right? So that is, so this is a completely different animal than the earthquake HVSR, right? This surface wave HVSR, just like your surface wave, it sample very small portion of the site, right? Very shallow portion of the site. So whereas the earthquake, when it comes through the entire part of the earth structure, it's sampling the entire material. So that is your body wave HVSR, right? So it's a body wave part. But MHVSR is basically surface wave part. If it is a surface wave part, I will be suggesting you to go from a little bit high frequency side, because it's sampling a very small area. So therefore the high frequency characterization you should also see in addition to the low frequency side, which is a much more deeper information. So always remember, the low frequency sampled the deeper earth, high frequency sampled the very shallowest portion of the earth. So you need to understand what you are measuring and how you are doing the things. So hardly your MHVSR data at a particular site will not match with your earthquake HVSR data, because their sample space are different, or the sample, it is sampling the completely different material, right? So you need to be careful on that. Don't try to get matched with this one, because if you get matched, you should be more surprised than if you do not get matched, because the or might be you can see the lower portion, lower frequency might be getting matched a little bit, but the high frequency are not. Okay, so that will be a significant observation for the HBSR. Now, as I try to tell you that whenever, as an engineering seismologist, whenever you try to do any this work, you should remember that the natural frequency of a building, if it is a 10-storied building, its natural frequency is 1 hertz, right? So basically, it's a very ballpark estimate. If it's a concrete structure, then it will be always n by 10. N is the number of stories divided by 10. So that is your a building natural frequency. So if it is a 10-storied building, n equals to 10, then divide by 10, so that will be equals to 1. So 1 hertz will be the natural frequency of a 10-storied building. এই তোমার এটা বন্ধ হয়ে গেছে। আবার বন্ধ। তুমি এটাকে একটা কাজ কত সকালবেলা কি যেন একটা করা হলো, না না ওইটা না, আমার মনে হয় হ্যাঁ ঠিক আছে, না এটা বন্ধ হয়ে গেছে। ওকে, না চলে গেল, বেশ ঠিক আছে। হ্যাঁ স্টার্ট করতে হবে। না দাঁড়াও, আমার মনে হয় এটাকে একবার অফ করে অন করে ভালো। Okay, so if you have a 10-storied building, then the natural frequency of a 10-storied building will be equals to n by 10. So if it is a n equals to 10 storied, then the natural frequency of a 10 storied building is 1 hertz. Don't always quote these things, but this is a very ballpark estimate, and this will be only valid for the concrete type of buildings, right? If it is a steel structure, it might change, okay? But on a ballpark, this is fine. So if it is a 2-storied building or 3-storied building, so 2-storied building means, huh? Oh, sorry, I take it back. This will be the frequency part, then it will be the 10 by 5 hertz. And this is the opposite thing. So just a minute. It will be the 10 by n. It will be the 10 divided by n. If it is the frequency, that's a period. So this is 10 by n. So 10 by n, so 10 storied by 10, 1 hertz. But if it is a 2-storied building, then the frequency will be equals to, for a 2-storied building, the frequency will be equals to 10 by 2, so around 5 hertz of the building, right? So 5 hertz means it's a 0.2 of second. So the period of vibration will be 0.2 second, right? So if it is a 100-storied building, then the natural frequency is, so how much? Uh-huh. 0.1 hertz, right? 0.1 hertz. So then it will be equals to, the time period will be equals to 10 seconds. So 10 seconds means it's a very high period, right? High period. So so you need to be careful about what frequency you are talking about for the soil sample, right? So if it is a 100-storied building, you have to construct, and in the soil, that soil has showing a 0.1 amplification, okay, then need to be very careful about, okay? So, or might be you need to take the proper precaution for your building to be retained during the time of a big magnitude earthquake, right? So now, so this is your amplification. So if it is an amplification, it will be mostly, if it is a 1, this is for the soil, then if it is for the rock, if it is this one, and then it will be amplified, means it will be always the greater than 1 value, but sometimes they show some less value than 1, so that means it will be showing some sort of a de-amplification at some frequencies, right? So that may be due to a lot of reason. A very low velocity sediment is located at some point or something like that. So that we also need to address. So sometimes this is happening, and also if there is a big earthquake, these are all analysis we are make it on a linear domain, right? So, but if there is a big earthquake happen in that area, then sometimes you will be seeing that the site response showing a de-amplification of the values at particular frequency. Some particular frequency around 5 hertz or so, 2 to 5 hertz, you might see that there is a de-amplification is happening, right? Now that de-amplification may be due to some of the soil liquefaction. So that means soil might be get liquefied under the tremendous pressure of the earthquake at that particular site, right? So if there is a site in reach of the sand which has a lot of water saturations and all these things that might happen in case of a big magnitude earthquake. Okay, so if there is a soil nonlinear behavior, we call it as a nonlinear behavior of the soil, and the linear behavior of the soil, this might be a totally different spectral response, right? So this is what we were trying to tell you. Now I had given you all the tool to cook for these things. So what I am expecting from you guys is this, that you have now the Fourier transform calculation, you have